Okay, so now in this last hour, I'll do a few applications of power series. The most important, well, not most important, but most popular one is using power series to evaluate indeterminate limits. Instead of the L'Hopital's rule, we use this one. L'Hopital's rule is easy when it is preferable when you look at the problem and you say, if I take apply L'Hopital once or twice, I'll get the answer. But then you realize that sometimes you have to apply the L'Hopital 7 times. Then nobody wants to do it, okay? Then you look at an easier way. So this one is easier than applying L'Hopital 5 or 6 times. Okay, so this is in using power series in indeterminate limits. Okay, so indeterminate limit is, remember this thing, limit of f of x over g of x as x goes to something. But in our cases, we'll do it, let's say a is equal to, and we have a picture like this. Okay, so you read this as a sentence. This says, so this is not 0 divided by 0, and for some reason I put it into parentheses. It's a sentence. It says that the limit as x goes to a of f of x is 0, of g of x is 0, and this much information does not determine what the actual limit is. Okay, you need extra information because we can find different functions here where the actual limit is 1, 2, 5, something, but all of them are of this form. So that's why the term indeterminate. This information does not determine the limit. So what you do, one method is use L'Hopital. Okay, so generally we use L'Hopital's rule. Okay, so this is actually Bernoulli's rule, but for some reason it is called L'Hopital's rule. L'Hopital did not call it his rule. L'Hopital just wrote a calculus book in which he wrote everything he learned from Bernoulli. L'Hopital was paying Bernoulli to teach him calculus, and he learned these things and then wrote a book. But he had his promise to Bernoulli that he would not publish them before Bernoulli did. Since he was going to publish it before Bernoulli, he didn't put his name. So the book came out with no author. And after L'Hopital died, the book was famous. After L'Hopital died, the publisher republished the book under the name of L'Hopital. Everybody knew that it was Bernoulli's rule, but for some reason we call it L'Hopital's rule. So naming in science is just a funny name, funny game. Okay, so anything can hold. Okay, so let's start, but we can also use infinite series. So the first example is limit x goes to 0 of sine x over x. We know that this limit is 1, okay, but how do we use infinite sums? So if you do this with L'Hopital, again, in one step, you get the result. But we have limit x goes to 0. Instead of sine x, I write the Taylor series of this. X cubed over 3 factorial plus x 5 over 5 factorial minus something. I divide it by x. So you see now you cancel these things. If you think about this a little bit, what L'Hopital is doing this cancellation. But L'Hopital does the cancellation one by one. Every time you apply L'Hopital, x is cancelled from both numerator and denominator. So if I had x to the 5 here and x to the 5 here, you can cancel it in one step. But when you take L'Hopital, this becomes x to the 4, right? You take the derivative, this becomes x to the 4, this becomes x to the 4. So L'Hopital canceled only one x. In the second application, it will cancel another x. So after 5 applications, you'll cancel all of them. If you have only functions like this, no problem. Okay, you can apply L'Hopital. But if this is this times something else, at every application of L'Hopital is split into 2. Sometimes there are signs, sometimes there are no signs. So it becomes unmanageable. In those cases, you don't want to apply L'Hopital, you apply this. Okay, so here, since when going, technically speaking, when we are taking the limit as x goes to 0, x is different than 0, so I can cancel. So what? So here cancel x. X goes to 0. So this becomes 1 minus x squared over 3 factorial plus x4 over 5 factorial minus something. And here you have 1. Okay, so now there's no problem. You just plug in x equals 0, you get a meaningful expression. So this is 1. So this is the typical expression, typical demonstration. Let's apply. So here you see it doesn't matter whether you write this one or L'Hopital. In fact, here L'Hopital is easier because you immediately see the derivatives. But when the leading term here is x to some larger power series is easier to apply. So let's see one example here. Okay, so here limit x goes to 0, tangent x minus x over sine x minus x. Okay, so we have to write the Taylor series. So here you have to apply L'Hopital 3 times. Okay, so you suspect it from here. Sine x starts with x. This cancels x. So the next term is x cubed here. Okay, so here the next term is also x cubed because this is an odd function. Tangent is an odd function. It starts with x, then it has x cubed, x5. You are canceling x. So both of them are x cubed. Okay, so if you want to apply L'Hopital, you have to apply L'Hopital 3 times. So this tangent will cause a little bit problem because its derivatives will just get larger. Okay, so let's apply power series. Power series of tangent x is something like this. 1 plus 1 over 3x cubed plus 2 over 15. This is 1 over 3 x cubed plus 2 over 15 x5 plus, all of them are plus. This is minus 1 over 6 x cubed plus x5 over 5 factorial. Okay, so in fact you don't have to write these things. You can put an asterisk here to remind yourself that all of those things have powers of x larger than 3. So you cancel. So this step, you can bypass this step because in your mind now you cancel x3s. So, okay, cancel x cubed. Then these cancel, and here you have 2, here you have 2. So all of them now have x in them. All of them here have x in them. The only things, numbers, are these things. So this is minus 2, right? Minus 2. After you cancel this. Okay, so let's do another one. So limit x goes to 0. Tangent x minus x times sine x squared divided by e to the power x. So what is it? E to the power x? Yes, x. Minus 1 minus x. And then I multiply this x and cosine x minus 1. Okay, so nobody wants to do L'Hopital here. Okay, so here the easiest way is to look at Taylor series. Sometimes in these things you stick in something like this, secant x here, okay, and then find me some other function which is, so say x cubed plus x plus 1, okay. So even if you are doing L'Hopital, you realize that these guys are not going to contribute indefinite objects. You calculate the limits of these separately. In these cases, the limit is 1 because when x equals 0, this is 1, this is 1. I could have put 2 here, so you take that. So let us also do that. Let's put 2 here. Okay. So the first thing to observe that that part is not contributing anything to the indeterminacy. You immediately calculate them. Okay, so this part, these tricks appear in the exam and also in your real life calculations. Sometimes you will have expressions like this. So it is important to separate which makes the expression indeterminate and which doesn't. Okay, so this part is not indeterminate. Its limit as x goes to 0 is 1 over 2. Okay, so the limit of this is 1, the limit of this is 2. So limit of a product is product of limits. So we come up like this. So this is, we take this out. Now we take here 1 over 2. Limit the rest. X goes to 0. Okay, so this one we did here. So let's write this. This is x cubed over 3. X cubed over 3 plus 2 over 15 x5 plus something something. And then this one, sine square, is x squared minus x6 over 3 factorial plus something something. Okay. Divided by, so this one. You see e to the x is 1 plus x squared over 2 factorial plus something something. Okay, so we carefully cancel these parts to bring out x squared here. So this is x squared over 2 plus x cubed over 6 plus these things. I have an x here. And I have cosine x minus 1 is x squared and minus x squared over 2 plus x4 over 24 minus something. Okay. So you see that I have x to the 5 here, x to the 5 here. You cancel x to the 5s. Okay, so you cancel this x3 with this and this. Okay, this and this. You cancel this x squared with this, and of course you are subtracting them here. And then you look at the coefficients. Since this is cancelled, these will all be 0. I have 1 over 3 here, times, here I'll have 1. I cancel these things, I'll have 1. Here I have 1 over 2, and here I have minus 1 over 2. Okay, so this is minus 4 over 3. Okay, so it always helps to have a few different techniques which apply to the same problem. And after you solve lots of problems at the beginning, when you are a student, you solve lots of problems, then you get a feeling about which method will be more favorable for that problem. Another way we apply Taylor series is to estimate if some given error, an exact antiderivative, I want the value for this thing. And you don't want the exact value. Even if the exact value is pi, you will use only the first few terms anyway. Okay, so estimation is reasonable. Okay, so for this, we check, so this is estimate this integral. So when we say estimate, of course, you should always come up with an upper bound for the error. Otherwise, estimation doesn't make sense. Okay, you want to estimate something whose actual value is 5. If you say 85 is an estimation, okay, that's an estimation. But what kind of precision do you want? Okay, so you have to tell that. So here we start. The idea is you take this function, you expand this Maclaurin series. We are around 0, so you expand the Taylor series around x equals 0. Then you use the fact that you can integrate that term by term. Okay? If you are lucky, you will obtain an alternating series. Okay? And then using the alternating series properties, you can sum a few terms and you know that the error is less than the next term. If it's not alternating, then you can use Taylor's theorem, which tells you what the error looks like. And then you find an upper bound for that error term. Okay? So that's the strategy. So let us look at how it works in this one. So I did these calculations, so let me quickly write them. So this is your general term will be powers of this. Your C coefficient, C is 1 over 2. So this is 1 plus 1 over 2 x to the 4 minus 1 over 8 x to the 8 plus 1 over 16 x to the 12 plus etc. Integrate. So you integrate from 0 to x again. And after that, I'll put x equals 0.2, 1 plus x4 dx. So this is x plus 1 over 10. Okay, so this becomes 5. 1 over 10 x to the 5. X to the 5 plus minus 1 over 72 x9 plus 1 over 208 x13 plus etc. Okay. Now put x equals 0.2. Okay. So this part, so I used only 3 terms. So this part is 0.2003. You will never use this much, but we still calculate these. 8, 8, 8, 4 tane 8 var, 4 tane 8, 9. Okay. And then you calculate this one. So this one is the same as these things, except that you have 0, 0 here, 39 something here. Okay, so these are all 0. So you see that the actual value is between this plus this and this minus this. Okay, so you see this changes. If this is all added to that, it changes this. If this is subtracted, nothing changes. So this part remains the same. Okay, so this is the value of this integral correct to this many 2, 4, 6, 8, 9, correct to 9 decimal points. Okay, so actually if you calculate it using other techniques, for example, in Maple, you calculate this saying that give me precision for 20 digits, then you see that this digit is also correct, so it actually changes this a little bit. Okay, so I'll do only one example here because I want to pass to the next thing. The next 2 things are interesting. This is called Machine. I don't know how it is written. He's an Italian, I think. John Machine's formulas. He lived in the 17th century. Remember, so the idea is now to approximate pi very quickly and very precisely. We already have a formula for this. We have an expression for arctangent x. But arctangent x, the general term, is of the form 1 over n, a coefficient divided by n. 1 over n goes to 0 very slowly. Okay, so if you want to obtain a precision like this, your n must be 10 to the power 10. Okay, you see, otherwise you will not have zeros here. If you want this much error, all of these parts must be 0, but 1 over n giving you all those zeros, n must be 10 to the all those numbers. Okay, so this gentleman found another way of, again using arctangent, but using addition formulas of tangent x to come up with interesting numbers to approximate pi. So that is one of the most interesting things where you use Taylor series. So you can look at Wikipedia. I think Wikipedia goes like machine-like formulas. Okay, so this gentleman is John, and he lived in 17th century, 1751, also in 18th century. So his calculations are as follows. So we start with this thing. Arctangent x, as we know, is x minus x cubed over 3 plus x5 over 5 minus, and the general term is minus 1 to the power n x 2n plus 1 over 2n plus 1 plus, and this works for x less than, actually less than or equal to 1. So this converges very slowly. So when you put x equals 1, you will get arctangent 1, which is pi over 4, and you'll have a convergence series for this. Theoretically, you can approximate pi to any degree of precision using this. But in practice, you see n must be very, very large so that 1 over n will be small. So, so to speed up the convergence, we observe the following. If you have tangent alpha plus beta, tangent alpha plus beta, this is equal to tangent alpha plus tangent beta divided by 1 minus tangent alpha tangent beta. If you have minus here, then this becomes minus, this becomes positive, but we know those things. Okay. Now we'll use this. Let x equals tangent alpha. So the idea is, instead of approximating pi with one arctangent, we'll say that it's pi is equal to sum of two arctangents using this formula. So let x be tangent alpha, y be tangent beta. And alpha is equal to, then alpha equals arctangent x, beta equals arctangent y. Okay. So this thing becomes, arctangent x plus arctangent y is equal to arctangent x plus y over 1 minus xy. Okay, so this is the great formula. So what is great about this? If I can find very small numbers, then arctangent x and arctangent y will converge very fast. Okay, so here, why this converge very slowly? Because we put x equals 1 here, and everything looked like 1 over n. That converges very slowly. If instead of x I put 1 over 1,000, then you see a cube of it, fifth of it, this would converge very fast. Okay, the error term will be very, very small after you use 2 or 3 terms. Then these things will converge very fast. But now the trick is I must recognize this angle. Okay, so that's what machine did. He sit down and tried lots of numbers, and he came up with some numbers. And I'll show you some of the numbers he found. Okay, so let's. Now, this is even an active area here. People in their spare time try to find x and y so that x and y are very small, and this angle is recognizable in terms of pi, of course. Okay? For example, if you choose x and y such that this arctangent of this number is, say, 60 degrees, and then you have an approximation for 60 degrees, and since 60 degrees is what, pi over 3, you can get pi. Okay, so that's what the idea is. Now put x equals, I think this is what, so no, this is not what machine did. This is Euler's formula. So Euler found this. Euler found the easiest one, I think, 1 over 2, and y equals 1 over 3. Okay. So now if you look at x plus y over 1 minus xy, this becomes 1. Okay. Put those numbers there, you get 1. So I can recognize the other part. That's arctangent 1. Okay, so you get 1. Okay, so let's give it a name. So from star, arctangent 1 over 2 plus arctangent 1 over 3. Okay, so is equal to pi over 4. Okay, so now the convergence is fast because I'm taking 5th power of 1 over 2 and 1 over 3. I'm taking 7th power. So x is small and x makes things go to 0 very fast. So the error term is small. Okay. Euler, remember, lived after machine 707, 783. So let's look at the actual numbers that machine himself used. Machine's formula is, of course, much better than this one, but you have to this part. Okay, he showed. Maybe I can go a little bit. 4 times arctangent 1 over 5 minus arctangent 1 over 239. Now you know it will converge very fast. Is equal to pi over 4. Okay, so it is this 4 that makes this a little bit more complicated. But this is, so here is how you find 4 arctangent 1 over 5. Okay, so you put these numbers in. So let me see what. Start with arctangent x plus arctangent x. Okay, so this is arctangent x plus x over 1 minus x times x. Okay, so this becomes 2 over here. Okay, so here, of course, x is equal to 1 over 5. We are trying to understand this. So this becomes arctangent 5 over 12. Okay, I want 4 of these things. So next arctangent x plus arctangent, arctangent, this 2, yes, now I want this one. Arctangent 5 over 12 plus arctangent 5 over 12. Okay, so remember that this is now equal to 4 arctangent 1 over 5. Okay, so this is now equal to arctangent 120 over 119. A very complicated number. We don't recognize it, but we don't have to recognize it yet, right? It is this part. Now I'll put it over here. Okay. So next we have next step by step. This is what for arctangent 1 over 5, which is equal to this. I subtract pi over 4 because I know this is arctangent. This is arctangent 1, right? Okay, so I again use that formula. Okay, so again let me put star here. So you put 1 over 5, you put 4 arctangent, this is equal to arctangent here. So here you put x equals 120 over 119 and y equals 1. Okay? And what you get arctangent 1 over 239, this number. Okay? So now you take it over there, you bring it over here. So this is clean thinking. Instead of trying to find what number I should put here so that I'll get arctangent 1, he just subtracts arctangent 1 here. Now whatever ugly number he gets here, that's the correct answer. Okay? So he doesn't have to search for this answer. The answer comes out with this one. Okay, so this is how you prove this one. So now you see that in this one, you can get pi very easily. So for a long time, this is such series were the only thing to calculate pi, but later on, different branches of mathematics found other faster ways of calculating these things. So the idea is this one. What is a power series? You have 1, x, x squared, x cubed. These are separate things. You have infinitely many of these things. We call them a basis. then you take a linear combination of this. Okay, writing a power series means that I take each of them and give them a coefficient. Okay, and you add them, you get something. But instead of using x and powers of x as a basis, I can use other things maybe. So that's what functional analysis is all about. In order to express this whole word, I use a different basis. Sometimes those different bases give you more faster convergent expressions. Okay? And then there are people who are obsessed in calculating pi. They come up with summation of rational functions. So instead of x, you have a complicated polynomial over polynomial. You put a coefficient to that, then you add another polynomial over polynomial. So that adds up to pi. You have to choose these polynomials so that, for example, when you calculate even the first term, you get pi to 6 or 7 terms correctly. The second term will give you pi to 20. There are people who devote their lives to calculating these things. So if you go to internet and write, how do I calculate pi, you'll have all those marvelous formulas. One thing nice about pi is you have to use some complicated algorithms to calculate it. So when you invent a new chip, or if you write a new software, your test bench is to check if it will correctly calculate pi. So that's the first thing they try in new computers. Okay, so let me finish this course by claiming and proving that this famous Euler number E is not a rational number. You cannot write E as the ratio of two integers. Okay, so nobody suspects that, but then you never know if this so we end up with the irrationality of E. Okay, so I think this is on one page. So we use the only thing we know about E is, well, we know a few other things, but the only thing we know computation-wise about E is the exponential series Ex. So this exponential function has 1 plus x squared over 2 factorial plus this thing as it's a Taylor series, and this converges for all x. Okay. Okay, this is not very useful in calculating E because you see I have to add these things. The only thing I can use is either Taylor's remainder formula or Lagrange's remainder formula integral, and it requires a lot of calculation. But if I have e to the minus x, then it will be an alternating series. The general term goes down to 0. So if I calculate the first 5 terms, I know how much error I'm making. Okay? Then e to the minus x is equal to, okay, these things cancel. You have x squared over 2 factorial minus x cubed over 3 factorial plus x5 over 5 factorial minus etc. So 1 over e is equal to 1 over 2 factorial minus 1 over 3 factorial plus 1 over 5 factorial. Okay, so this is, and the general term, so I need the general term in this minus 1n, 1 over n factorial. So this goes like this. So I can calculate 1 over e. If e is rational, then 1 over e is also rational, right? So that's what we will say.
Shouldn't what we write as 5 before? X to the power 5 and 5 factorial we write, but shouldn't before?
Yes. 4 factorial, yes, you are right. So we play so much with tangent and sine that it's stuck in our minds. Okay, now if E is rational, then so is 1 over E. So assume 1 over E is equal to R over S, where R and S are positive integers and their greatest common divisor is 1. Okay, so we write it as a rational number, cancel out the common factors. We have this. Now, if I add a few terms, then you see if I add up to here, the number I get is larger than 1 over s, because the last thing I did was add this. Then if I add one more term, it will be less than this. So let n be the largest odd integer, less than or equal, larger than or, I don't want largest, I just want any, let n be an odd integer larger than s. Okay, so that's all I know. Let n be an odd integer larger than or equal to s. Okay, any odd integer will do. Because I want to add up to n, then it will be minus. So that sum will be less than 1 over e. That's what I want to use. Okay, so then I have this 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus, and then the last thing is minus 1 over n factorial. Okay, so this is odd, therefore this is minus. This is less than r over s, and this is less than 1 over 2 factorial minus 1 over 3 factorial plus etc. Minus 1 over n factorial plus 1 over n plus 1 factorial. Okay, so this part is the same as this part. I add one more term. According to the rules, it must be strictly larger than r over s. Now I multiply both sides by n plus 1 factorial. Okay, so let me finish it over here. Okay, multiply both sides by n plus 1 factorial. Okay, so observe that n plus 1 factorial times 1 over 2 factorial minus 1 over 3 factorial minus 1 over n factorial equals a is an integer. Okay, so these are all numbers smaller than this, so they cancel themselves and you get an integer. Okay. N plus 1 factorial r over s is b is another integer, because n plus 1 is larger than s, so s cancels itself. And then n plus 1 factorial 1 over 2 factorial minus 1 over 3 factorial minus 1 over n factorial plus 1 over n plus 1 factorial is equal to, this part is a plus 1. Okay, so we found two integers. We found that we have a less than b less than a plus 1. Okay, so this is an obvious contradiction. There's no integer in between two integers. Okay, so there cannot be an integer in between two consecutive integers. Okay, so this contradiction says E is not rational. Okay, so in fact we know a lot, well, this much we can prove using easy calculus. Again, using calculus with everything we learned so far, we can prove that E is not algebraic. So what is algebraic? Because the numbers, so the numbers are first, real numbers are first separated into two, rational and irrational ones. If it cannot be written as r over s, it is irrational. But irrational numbers turns out to be into two classes. We have one class, okay, so it is, if you have a polynomial p of x with integer coefficients. Okay, roots of such px are called algebraic numbers. Okay, so algebra always involves polynomials, are called algebraic. If not, if a number, real number, is not a root of a polynomial, root of such a polynomial, such as with integer coefficients, such a polynomial, it is called transcendental. Now let's think about this. Which numbers are more? Do we have more algebraic numbers or more transcendental numbers? If you have polynomials with integer coefficients, first consider, first of all, list these polynomials according to their degree. Given any degree, there are countably many polynomials of that degree because the coefficients are integers. Integers are countable. Okay, so there are countably many linear polynomials. There are countably many cubic polynomials with integer coefficients. So all polynomials with the integer coefficients form a set of countable set. Each of them has finite many roots. Okay, so all algebraic numbers, the set of all algebraic numbers is countable. The set of all rational numbers obviously countable, but real numbers are uncountable. Okay, so what remains apart from algebraic things is transcendental numbers. So transcendental numbers are everywhere. So the allegory is that when you look at the sky at night, the stars are either rational numbers or algebraic numbers. All rational numbers are algebraic numbers, okay, in a linear expression. So the stars are like algebraic numbers and the darkness is the transcendental number. So that's how these things work. This is how you explain it in everyday life. In mathematics, we say transcendental numbers are dense in real numbers. So if you arbitrarily pick a number, it should be transcendental. But nobody can write a transcendental number easily because if you write something, even if it's a digit, you'll stop somewhere. It's a rational number. Okay, so the only key at that time. But then the first, you see, by just logic, you know that there are uncountably many transcendental numbers that produce one. So it was a big problem. So the first transcendental number produced was something like this, 0.1. Then you put 0 here, 1, 2 zeros, 1. So from 1 and this one, you put n factorial zeros here. Okay, so this thing, you make this. So I think Liouville was the first person who constructed. Then he showed that this is a transcendental number. Okay, then the question is pi transcendental? Is E transcendental? So E is transcendental. But its proof can be done again in calculus, but it takes some time. So I'll just write here that E and pi are transcendental. The proofs are not complicated, but you have to read over them slowly because they are using only the things that we know, but in a very strange. I think the proof of pi may use a little bit more complicated thing, but you see, with the calculus you learned so far, you can now understand these things. Okay, so let's stop this calculus here. Thank you for coming. See you next year or other year in higher courses of math. Okay, thank you.